Okay, so this one we're going to have a little look through, and we're going to look at precision. When we are finding precision, we are going to be looking at our percentage equipment uncertainty. Okay, so when we're finding precision, first of all, you need to look at whether or not you have an analog or digital piece of equipment. If it is analog, then you want to look at your smallest reading, generally. So if this is a thermometer and this was 1 degree and this was 2, you see each of these divides is going to be 0.2 degrees. My uncertainty is going to be half of that, because we can see if I have a line there, we can see if a line is hitting one of the marks or if it's between a mark. So this one here, we would be able to see it's between two of the marks. So we would be able to estimate, not estimate it, we would be able to give that as 1.7. Okay, as a result. So analog, it's half the smallest increment. And with digital, you just need to read the value off the reading, and it's precise to the number of digits on the reading. So this one, this balance here, I've badly sketched. It's not reading anything here, but it's accurate to 2 decimal places. So this one would be plus or minus 0.01 grams, because it's accurate to the nearest 0.01 gram. Accurate is maybe not the right word in this case. Okay, so once you have your equipment uncertainty, and remember to write down the units when you do that, to calculate your percentage equipment uncertainty, you are going to take whatever your measurement was. So I'll use my example from here. That was 1.7 degrees. And I'm going to take my uncertainty. Oh, I've put this upside down. Sorry. I'm going to take my uncertainty 0.1, and I'm going to divide that by the reading and times that by 100. That would give me a percentage. Okay, and you need to do that because let's say I've measured something with my thermometer and I've weighed something as part of my experiment. I can't add those two together. I can't add something in degrees to something measured in grams. That just doesn't work. It's nonsensical. But if I've converted it to a percentage, I can now add them up. Right, once you have your percentage uncertainties, you can add them together, but before I get on to that, we just need to make sure that you understand that if you are ever doing a change in a measurement, so let's say you were doing a change in temperature or a change in mass, so you measured before and after, that will double your uncertainty. Okay, so the reason for that being, I'm going to use very kind of simple example for this, our thermometer again. Okay, and I'm going to say each of these is 1 degrees. So if my first reading was 2 degrees, so my initial temperature was 2 degrees, okay, that means that the real reading, because this is plus or minus 0.5, the real value is anywhere between 1.5 to 2.5. Okay, that's what the plus or minus 0.5 degrees means. And let's say we do it that the experiment and the temperature goes up to 5. So my final temperature is 5, and again this is going to be plus or minus 0.5 C. So that means that this is anywhere between 5.5 and 4.5. Okay, so when you look at this, the maximum change in temperature that these values could be is the difference between these two. So the maximum change in temperature is 4 degrees, and the smallest change in temperature is the difference between these two, which is 2 degrees. Okay, so our change in temperature was 3 degrees, but it could be anywhere up to 4 or anywhere down to 2. So that is plus or minus 1 degree. Okay, see, we've doubled that uncertainty. So you have uncertainty at the beginning and an uncertainty at the end, and those uncertainties add together. So with uncertainties, if the transformation you're doing, the calculation you're doing is adding or subtracting, okay, then it is just the sum of the measurement uncertainties. And this only really applies, I mean, I can't think of any examples. Can't really, maybe if you're adding liquids together. So you've got, you're kind of diluting down, maybe you might be able to add the uncertainties for that. But if the calculation you did involved an subtraction or an addition, then you can just, the measurement uncertainties, just add them together. You don't have to transform them. Now, if the calculation you're doing involves multiplying or dividing, then you have to add together the percentage uncertainties. Okay, so you've got to do the conversion first to a percentage, and then you can add them. I'm going to add a caveat here. Please be careful with pH, because that is a logarithmic scale. So when you're using that, there's a special equation for it. And if you're doing exponentials, the calculation is different again. So this bit is only in the HL specification, but if this is your IA, so you should be doing stuff beyond your specification. If you are doing exponential, so whatever your value, if it's to the value of A, you then need to times your uncertainty by A. So if you're ever doing an exponential, you need to be careful. There is a separate equation for pH because that's a logarithm. So I am going to just give you a little warning here. If your IA involves pH, you need to be careful when calculating the uncertainty in pH. There are some more than one way of doing it. So provided you reference the way that you are using, that's fine, but please go and do some research before doing that. So for the last bit here, thinking about your conclusion or evaluation, one of the things you consider is your precision. And we've got the 2 ways of improving your precision. So more precise equipment, but let's say you had a bunch of readings. I think I mentioned this in another video. So if we have an uncertainty from a balance and a measuring cylinder and a stopwatch, and those look something like this, which isn't unfeasible. If you're measuring for 10 minutes, stopwatch is going to be very low uncertainty. There's no point using a balance to 3 decimal places or 4 decimal places, because relative to the measuring cylinder, it's negligible. So focus on whichever equipment gives you the largest percentage uncertainty. And this is why it's also worth making it really clear in a table somewhere what your percentage uncertainties are. So that's one way of increasing your precision as in your evaluation. The other way is to increase the size of your measurement. Okay, so that might be thinking of if I was doing the of combustion, if I burn a larger amount of fuel, I'll get a bigger temperature rise. So that would reduce the uncertainty on the mass change and reduce the uncertainty on the temperature change. There's obviously a limit with that. You can't go higher than the boiling temperature of water, for instance. So there is a bit of a caveat on that. I might, if I want to get a larger burette reading, so let's say my burette reading was something like 3.5 cubic centimeters from my burette, that would be a very high uncertainty. So I'd want to get a larger reading. I could use a more dilute titrant. Okay, so if it was 10 times more dilute, that would give me a titer of around 35. Let's say it was acid, 0.1 molar instead of 1, I'd have 10 times the volume, but I can't do anything that makes this greater than 50 cubic centimeters, or it would be bigger than the volume that the burette can use. Okay, so you need to be sensible with this when you're thinking through your improvements. So that's how, first of all, you assess your precision, and then how you look at your precision and specifically work out how you can, in your evaluation, make improvements.